Okay, chapter 17, next chapter that we're going to try to get through as much information as possible before next week. And chapter 17 is titled The Additional Aspects of Aqueous Equilibrium. Now, one of the things that we have with this chapter is this thing called a common ion effect. Well, what is a common ion effect is when we have a weak acid or weak base and a salt that have a common ion in them. Excuse me. So, example, our weak acid, acetic acid, CH3COOH. Salt, sodium acetate, CH3COONA. So if we take both of these through dissociation, I'm breaking them apart, acetic acid, we get our hydrogen ion and we get our acetate ion. Sodium acetate, if we take that apart, we get sodium ion and acetate ion. So our common ion is acetate. Okay, now, looking at our weak acid, what we learned with the last chapter is we can calculate out our pH of our weak acid by going through the ice table and everything. But if we have a presence of sodium acetate in our solution with the acetic acid, the presence of the added acetate ion causes the acetic acid to ionize less. Okay, which means that our acetate ion would not dissociate into hydrogen ions and acetate ions. It would stay more as acetic acid. And if this happens, then what we kind of see is that less ionization means that the pH wouldn't be as low as possible. So let's kind of look at an example of this. What is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution? Alright, so we're going to set up our ice table. Okay, so now we have a 1 liter solution and we have 0.3 moles of acetic acid and 0.3 moles of sodium acetate in there. So our initial concentration, well, acetic acid, 0.3 over 1 is going to be 0.3 molar. Now looking at sodium acetate and acetic acid, our common ion is the acetate ion. So at the initial we do have some acetate ions floating around, and its initial concentration is going to be 0.30 molar as well. Hydrogen ion, its initial concentration is going to be 0. So if we go through our change, since we have 0 over on the right hand side, change is going to be positive there. Reactant side, change is going to be negative. Now, I forgot to write down what is the K of A acetic acid, so let me look that up real quickly for you. Okay, acetic acid, K of A is 1.8 times 10 to the negative fifth. Alright, so just like what we're doing with the last chapter, K, or with the acid-base chapter, not last chapter, excuse me, K of A is equal to hydrogen ion times acetate ion all over concentration of acetic acid. Alright, K of A is 1.8 times 10 to the negative fifth is equal to X times 0.30 plus X all over 0.30 minus X. And what we learned with the acid-base chapter, if our K of A is really small, then we can negate our plus and minus X's in this situation. So if we can cancel those out, now if we look at it a little bit more cleaned up, we can also cancel out those 0.3s because 0.3 over 0.3 is 1. So X is equal to 1.8 times 10 to the negative fifth. And that is our hydrogen ion. So if we want to find the pH, negative log of 1.8 times 10 to the negative fifth molar, and that comes out to be 4.74. Alright, so let's look at another example of this. Alright, it says, calculate the fluoride ion concentration in the pH of a solution that is 0.2 molar hydrogen fluoride and 0.1 molar HCl. And we're getting the K of A for HF as 6.8 times 10 to the negative fourth. Let's set up our ice table. So we have initial concentration of HF, 0.2 molar. Okay, now, our solution also has HCl. The common ion between HF and HCl should be the hydrogen ion. So we're going to have initial concentration of hydrogen ion as 0.10 molar because that's coming from the HCl. Fluoride, initial concentration is going to be 0. So change for HF is going to be negative X, so 0.2 minus X. For hydrogen ion and fluoride is a plus X. So at equilibrium for hydrogen, we're going to have 0.10 plus X, and for fluoride, it's just going to be X. So we're going to take 6.8 times 10 to the negative fourth, and that's going to be equal to 0.10 plus X times X all over 0.20 minus X. Is our K of A small enough? Yes, it is. So we're going to cancel out those plus X and minus X. 6.8 times 10 to the negative fourth is equal to 0.10 times X all over 0.20. So we can find out that X is going to be equal to 6.8 times 10 to the negative fourth times 0.20 all over 0.10. And what does X come out to be numerically? So 6.8 times 10 to the negative fourth times 0.20 divided by 0.10. I'm coming up with 0.00136 for an answer. So that is our fluoride ion concentration. Now the pH. Okay, well, if we look at our hydrogen ion concentration, at equilibrium we have 0.1 plus X. Do you think we're really going to have that much of a change in the pH? We're starting off with 0.1 and we're adding 0.00136. Hopefully in your mind you're saying no, and that would be correct. So pH, negative log 0.1. Now this would be right around pH of 1. Okay? Now, kind of keep on going to kind of help you out with this. Along with this, we can talk about buffers. Now, this is a lot of information. So instead of reading it to you, you're all old enough, big enough, whatever you want to say, to read all this information. Okay? One of the things I want to talk about with you quickly is how we can calculate the pH of a buffer solution. Now, if you didn't know that you do have a buffer solution in your body, it's in your stomach. So the way that we usually calculate out the pH for a buffer is we can use what is called the Henderson-Hasselbalch equation. And the pH is equal to the pK of A plus log of the concentration of the base over the concentration of the acid. Alright, so let's look at two examples. So what is the pH of a buffer that is 0.12 molar lactic acid and 0.10 molar sodium lactate? And the K of A for lactic acid is 1.4 times 10 to the negative fourth. All right, so if we use the Henderson-Hasselbalch equation, pH is equal to pK of A plus the log of concentration of the base over the concentration of the acid. Okay, pK of A. Well, how do we find the pK of A? We take the anti-log. So the pK of A, the anti-log would be 10 to the negative 1.4 times 10 to the negative fourth plus the log. Now, which one is our base? Well, we have lactic acid. Wonder which one that's going to go to, and sodium lactate. So lactic acid is going to be our acid. Sodium lactate is going to be our base. So we're going to have 0.1 molar over 0.12 molar. So if we take the anti-log of 1.4 times 10 to the negative fourth, wait a minute, excuse me, sorry, it's not the anti-log. Brain fart right there. pK of A, we take the negative log of the K of A. Sorry. Once again, I'm having a brain fart today. So pK of A, negative log of 1.4 times 10 to the negative fourth. Negative log 1.4 times 10 to the negative fourth. There we go. In my mind, I was thinking it was wrong. So 3.85 plus log of 0.10 molar over 0.12 molar. Okay, so 3.85 plus. Now, if we take the log of 0.10 divided by 0.12, come up with negative 0.079. So 3.85 plus negative 0.079, pH comes out to be 3.77. Now, how could we possibly kind of check this? Well, we could run through the ice table of dissociating lactic acid, and the common ion would be the lactate ion, and go that route and see what we come up with. But this is kind of a shorter route that we can possibly take. Okay. I'm going to stop here for right now because I got to switch out batteries because I'm about to die. So I'll be right back with you.